Okay, so here's another implicit differentiation problem. We did this one with the circle. We came out with the derivative we thought we would based on the Desmos article or activity we did. So here we have a function, uh, or not a function, some type of relation, some weird thing. I don't know. I have no idea how this graphs actually. Y minus x equals e to the xy. I don't know what that looks like. You can put it on Desmos, see what it looks like. That would be cool. In fact, at the end, maybe we should make sure that whatever we find out for our answer is what we think it is visually. So we have this relationship. It says find the derivative of the function in terms of x at the point xy -1, 0. Well, that implies we're looking for the slope of the tangent line. We're looking for the slope of the tangent line at -1, 0. -1, 0 better be part of the function. So before we go too far, let's just make sure that it is. If we put -1, 0 in, is this true? Let's see. Y is 0, negative of -1, so this side is 1. Y is 0, negative of -1, so this side is 1. That makes sense. And then e to the xy, well, if y is 0, this is basically e to the 0. E to the 0 is 1. Anything raised to the 0 power is 1. So 1 equals 1, so that's good. So this point is actually on the graph, and we're looking for the slope at that point. So we're going to differentiate implicitly. In fact, we couldn't even solve for x for y if we tried. Here, I had you solve for y once, so we did it implicitly. Or we did it explicitly, rather. We did both things. But here, we can't get y by itself on one side, so we have to do implicit differentiation. We have to just trust this process and differentiate with respect to x, regardless of what we have. So the derivative of y is dy dx. The derivative of x is 1. And then we have this little function, which typically isn't very complicated, but here it's a little weird. E to the xy, e to the anything is e to the anything times the derivative of what's inside. So we have e to the xy, there's our beginning, times, we have to take the derivative of x times y. We have the product rule here. So we're going to have two things added together. We're going to take the derivative of one times the other, and then we're going to add to it the derivative of the other one times whatever we started with. So let's do derivative of x. Derivative of x is 1 times y plus the, now we have to do it the other way around. The derivative of y is dy dx, right? Dy dx times x. Okay. So here we took the derivative of x times y, and then we took the derivative of y times x. Okay, so that's good. So now we have this function. I suppose we could just plug this in right now and solve for dy dx, but I'm going to solve for dy dx and put it as a kind of a function first. So let's get dy dx together. In order to do that, let's distribute this first. So let's see, dy dx minus 1 equals e to the x times y. So that's y e to the xy. E to the xy times y is y e to the xy. And then e to the xy times x dy dx is, let's see, I'm going to write it this way, x exy dy dx. So x times ex to the y times dy dx. All right. Now, if I want to get dy dx by itself, I'm going to get those two terms on the same side and factor out anything else. So let's bring dy dx over here and get everything else over there. So let's see, we have this dy dx, this one, and then we have to subtract this one, minus x e to the xy dy dx equals, let's see, we're going to have to add the 1 to both sides. So we're just going to wind up with y e to the xy plus 1. Okay, so now we have to factor out the dy dx. So dy dx times 1 minus x e to the xy equals y e to the xy plus 1. And then in order to get to dy dx, we got to divide by this. So I'm going to put this up here. So dy dx equals, let's see, it's going to be this divided by this. So y e to the xy plus 1 over that 1 minus x e to the xy. Okay. Now, depending on how you do this, you might get things that look different than that. They might be in different forms. I did a little while ago. I got something that looks very different than that. I hope the answer comes out the same. God, I'm praying. I had 1/2 before. So let's see what happens. Now to find dy dx when xy equals -1, 0. We need to plug -1, 0 into all these places. So dy dx at x, y equals -1, 0 is equal to, let's see, y is 0, right? I'm plugging in y, I'm plugging in 0. So y is 0, so this whole thing is 0. So in the numerator, we wind up with 1 because y is 0 and that all goes away. In the denominator, we wind up with 1 minus x times e to the xy. Now, e to the xy, this y is 0, so it doesn't really matter much what x is, because as soon as the y is 0, we wind up with e to the 0. E to the 0 is 1. So what we have here is 1 minus -1. 1 minus -1 is 2. 1 minus -1 is 2. So there is an example of a much more complicated implicit differentiation problem where you're asked to find the tangent, the slope of the tangent line at a particular point of a weird function. Now, if you want to go to Desmos, you can type that function in just like that. You don't have to change it at all. You can type that function in and it will graph it. It knows how to graph stuff all over the place. It doesn't matter if it's solved for y or not. And then you can take a line. Let's see, what would be the slope of the tangent line? What would be the equation of the tangent line at that point? Well, that's easy. That's y minus 0 equals, here's your slope, 1/2, times x plus 1, right? So take a look and see if that tangent line is actually tangent to that function at that point. And you'll kind of be proving out that what we're doing actually works. I have a feeling it does, although I haven't checked it. So why don't you check it? See what happens. Should be fun.